Hi, my name is Vincent, and I am from the Speech and Audio Processing Lab in Imperial College London. In this talk, I will be presenting our ICASSP2020 paper titled PEVD-based Speech Enhancement in Reverberant Environments. This is the outline of my talk today. The single-channel and multi-channel subspace approaches for speech enhancement use an EVD to decorrelate spectrally and spatially respectively. However, an EVD can only decorrelate instantaneously. Other methods typically uses the short-time Fourier transform for processing. This uses the DFT to divide the broadband into multiple narrowband signals. However, this approach lacks phase coherence across bands and ignores correlations between bands. To capture the space-time and frequency correlations using a three-dimensional tensor, polynomial matrices are introduced as an appropriate model. To process them, polynomial EVD are used to impose spatial decorrelation over a range of time shifts without introducing any phase discontinuity. In our earlier work, we proposed a polynomial EVD-based speech enhancement algorithm and have demonstrated its effectiveness in anechoic environments. We have shown that its performance approaches the Oracle multi-channel Wiener filter, which uses complete knowledge of the clean speech signal, and our approach does not introduce any noticeable artifacts. In this talk, we will focus on speech enhancement in reverberant environments. Consider the following signal model, with X representing the received signal from M sensors. H is the channel impulse response. S0 is the anechoic speech that is uncorrelated with V, the additive noise signals at the sensors. Assuming stationarity, the space-time covariance matrix RXX is computed using the received signals X. More specifically, each element is the correlation function between sensor pairs. And its Z transform gives us a parahermesian polynomial matrix. In this talk, we will use calligraphic font to denote a polynomial matrix and regular font for matrix. The PEVD is defined as the following, where capital lambda and U represents the eigenvalue and eigenvector polynomial matrices respectively. The superscript P denotes the parahermesian operator that involves the Hermitian transpose operation followed by a time reversal. The eigenvector polynomial matrix U can be interpreted as a filter bank, which produces output Y that are strongly decorrelated. To perform the polynomial EVD, one of the following algorithms can be used. In multi-channel signal processing, one typically computes the spatial covariance matrix, which is given by the outer product of the input signals, and this can be seen as a special case of the space-time covariance matrix when tau is equals to 0, and hence it's sometimes called the instantaneous spatial covariance matrix. By computing the correlations at all time lags and taking the Z transform, we obtain the following polynomial matrix. Observe that for this example, only the plane at the 0 lag is diagonal. The goal of the PEVD algorithm is then to diagonalize at all lags. Note that because the different planes are coupled, we cannot simply apply individual EVDs at different planes independently. The polynomial matrix can be interpreted as a polynomial with matrix coefficients, shown on the left, or equivalently, it can be interpreted as a matrix with polynomial elements. Let's take a look at the same example before and after diagonalization. On the left, the Z transform of the spacetime covariance matrix is computed using the correlation between sensor pairs. So in this case, we will get the autocorrelation terms on the diagonal. So this will be the autocorrelation of sensor 1, 2, and 3, whereas the off-diagonals are computed based on the cross-correlation between sensor 1 and 2, 1 and 3, 2 and 3 in this case. And on the right, after we have applied the polynomial EVD algorithm, we end up with this diagonalized eigenvalue polynomial matrix, capital lambda of Z. And the off-diagonal elements at all legs are now zeroed off. In our earlier work, we only consider direct path propagation only, which is relevant for close talking speaker to the microphone and anechoic environments. In distant talking scenarios and enclosed rooms, such as voice-controlled home systems, multipath reverberation must be considered. The reverberant channel can be decomposed into the direct path, early and late reflections, as shown in red and blue, using a typical example of a room. The early reflections are closely spaced echoes which have a direct path strengthening effect and may improve speech intelligibility under certain conditions, whereas the late reflections comprise randomly distributed small amplitude components, which makes the blue term uncorrelated with the red terms. Hence, this term here can be treated as an additive noise component. We can then rewrite the signal model by incorporating the reverberant channel to give us S tilde and V tilde, which are uncorrelated. Then the goal here is to obtain an enhanced version of the speech using the microphone observations X. And the enhancement target can be one of the following: to reduce noise, or to improve speech intelligibility and quality. Since S tilde and V tilde are uncorrelated, the polynomial EVD decomposes the signal into the signal and noise subspaces, which are orthogonal. For a single speaker scenario, the denoise and enhanced signal can be recovered by a weighted reconstruction in the subspace. The speech enhancement algorithm is summarized here. Using the microphone signals, we first compute the spacetime covariance matrix. So the on-diagonal terms are the autocorrelation functions, and the off-diagonals are the cross-correlation functions. So this will be between sensor microphone 1 and microphone 2, microphone 1 and 3, 2 and 3, followed by the Z transform, which gives us a polynomial matrix. This is then used as the input into the polynomial EVD algorithm, which produces the eigenvalue and eigenvector polynomial matrices. The microphone signals are then passed through the eigenvector filter bank, and then we can recover the enhanced signal in the first channel by reweighing the subspace components. We now demonstrate an example of reverberant speech signal arriving at 3 microphones and corrupted by 0 dB babble noise. The speech signal is produced from the timid corpus, while the lecture room impulse response and the noise signals are obtained from the ACE corpus. In this case, the T60 of the room is 1.22 seconds. We then compared our proposed polynomial EVD approach against 2 subspace approaches. So one is based on the colored noise, and the other is the multi-channel subspace method, as well as against the log MMSE, and 2 versions of the multi-channel Wiener filter. The first version uses the relative transfer function, RTF, and noise estimator, and this is what is used in practice. The second version is what we call the Oracle Multichannel Winner Filter, which has the knowledge of the clean speech signal and establishes the upper bound performance. We then evaluate the algorithms using the following metrics. The results of the algorithm for a single example is summarized here. For this example, Polynomial EVD was able to simultaneously reduce noise and improve the speech quality and intelligibility significantly. Colored noise and log MMSE offer significant noise reduction. However, this was achieved at the expense of introducing speech distortion, as indicated by the negative Stoy and Pesk scores. MWF offers some noise reduction, but not much improvement in the speech intelligibility and quality. The Oracle MWF performs the best in terms of Stoy and Pesk because it uses prior knowledge of the clean speech signal and is designed to minimize speech distortion. Here, Polynomial EVD performs competitively, while bearing in mind that the PEVD approach is a blind algorithm and is able to achieve substantial noise reduction. Let us listen to some audio files. Of course, it may be difficult to hear the differences on this video recording, so I will be providing the link to the listening examples at the end of the talk. Here is the noisy signal.
Knife-like pain in his groin and brought him down. Very peculiar attribution of D as to overtakes as Joker. Groundhog clearly saw a chef, stayed out.
The colored noise.
Knife-like pain in his groin and brought him down. Very peculiar attribution of D as to overtakes as Joker. Groundhog clearly saw a chef, stayed out.
Log MMSE.
Knife-like pain in his groin and brought him down. Very peculiar attribution of D as to overtakes as Joker. Groundhog clearly saw a chef, stayed out.
Let us hear the noisy signal again before listening to the rest.
Knife-like pain in his groin and brought him down. Very peculiar attribution of D as to overtakes as Joker. Groundhog clearly saw a chef, stayed out.
The Oracle MWF.
Knife-like pain in his groin nearly brought him down. Very peculiar attribution of D seems to overtake such jokers. Groundhog clearly saw a shadow, stayed out.
Now I will play the noisy, followed by Polynomial EVD.
Knife-like pain in his groin nearly brought him down. Very peculiar attribution of D seems to overtake such jokers. Groundhog clearly saw a shadow, stayed out.
Polynomial EVD.
Knife-like pain in his groin nearly brought him down. Very peculiar attribution of D seems to overtake such jokers. Groundhog clearly saw a shadow, stayed out.
In this talk, I've introduced polynomial matrices and polynomial EVD as a tool for processing them. I've then outlined a PEVD-based speech enhancement algorithm designed for reverberant environments. The proposed method exploits the lack of correlation between the speech and late reflections for further noise reduction, and it incorporates the early reflections to further improve speech intelligibility and quality. The proposed approach does not introduce any noticeable artifacts, and it does not use any noise estimator. These are the references used in this talk. Thank you for your attention, and the listening examples can be found by scanning the QR code, or you can key in the URL. Also, please visit the webpage to get the materials and videos for my work. Thank you.